Let's start chapter 2 and introduce Lebesgue measure. So the plan is in this section to give sort of a wish list of properties of a measure. Lebesgue measure won't satisfy this wish list of properties, not all the properties, will weaken one of them. In fact, it can be shown there is no measure that will satisfy all the desired properties. So the plan is, the big picture is, I want to generalize Riemann integration. We'll do so by generalizing the idea of the length of an interval. Riemann approaches integration by partitioning up an interval, drawing rectangles, as it were, with bases determined by the widths of those rectangles and heights determined somehow or other from function values. So what we're going to do is, similar to that, we'll still be thinking rectangles, and we'll determine heights from function values somehow, but the bases are going to be different. They won't be little intervals anymore, they'll be little sets. So we won't weigh those sets by their length, we'll weigh them by their measure. And we want this measure idea to reduce to the idea of length so that we'll get Lebesgue integration to be a generalization of Riemann integration. And we'll get the measure of a set to be the generalization of the idea of the length of an interval. Okay, so the plan is to weigh an interval by its length. That's how Riemann does it. So to generalize the Riemann integral, we desire a way to weigh sets other than intervals. The weight should be a generalization of the length of an interval. Here's this idea again. We know an open set is a countable union of disjoint open intervals. So we might define its weight, an open set's weight, its measure, that's where we're going with this, to be the sum of the lengths of the open intervals which compose it. I made a big deal out of knowing what an open set of real numbers looks like, and we're using it already here, and we're barely 2 or 3 paragraphs into the motivation of Lebesgue measure. So we're trying to generalize the idea of a length. Hey, open sets, they're made out of intervals, they're made out of disjoint intervals. I can find the lengths of those intervals and we can add them up. I might have a little bit of concern about divergence, more of that here right now. Okay, so that's the plan. There's how we would measure open sets, taking total advantage of the fact that we know what an open set of real numbers looks like. Countable disjoint union of open intervals. They're made out of open intervals. We want a function M that maps the collection of all subsets of the reals. We will fail on that count. That is defined on the power set of the reals. And it maps us into the positive real numbers along with 0 and the infinity symbol. If you like, and well, even if you object, and I object a little bit. This is denoted as the closed interval from 0 to infinity, including infinity. We're in the extended real numbers here. There's some information on that in chapter 1. As long as we don't do arithmetic with the infinity symbol, we can use it as an image of certain kinds of sets under this mapping M. So we're trying to associate a real number, a non-negative real number, or the infinity symbol with every set of real numbers. And this is a weight that we're putting on those sets. And we want this weight to be somehow related to the length of an interval. We want it to be the length of an interval when we have an interval, because we wish this mapping, lowercase m, measure, to satisfy the following 4 properties. For any interval, we want the measure of that interval to equal its length. We use this little calligraphy L to represent the length of an interval. So we desire that the measure of an interval be the length of that interval. I already need the infinity symbol because some intervals are unbounded. So we're allowing, of course, measures of sets to be infinite. The measure of the whole real numbers. The whole real numbers is an interval. And the measure of the whole real number line should be infinity as well. For all sets E on which M is defined, and for all Y, a real number, we require that the measure of E plus Y equals the measure of E. This is called translation invariance. And what we've done is taken set E over here and translated it by an amount Y over here. Well, that's an odd thing to think of, but yeah, of course, I don't want the measure of a set to depend on where it is. I don't want to take a set that's close to the origin and has a certain measure and then slide it out far away from 0 along the real line and let it take on different values. This is a rigid translation. We've simply added Y to every element of E, is what the highlighted stuff means. So you're simply taking the set and translating it by an amount Y. Of course, you don't want that to change the measure. I want the measure of these two sets to be the same. Translation invariant or translation invariance of M. Thirdly, if E sub K, notice it's countable collection, a sequence of disjoint sets on each of which M is defined, then the measure of the union equals the sum of the measures. We're using this little union dot symbol to indicate that it's a disjoint union, not an entirely universal symbol, an awfully useful one in this real analysis stuff. We will deal quite often with sequences of sets. Sometimes they'll be disjoint, sometimes they won't. Well, if we union them up and they're disjoint, I'm putting a little dot inside that union symbol. One argument that this isn't a very universally used symbol is it's not a LaTeX command. It's not a standard LaTeX command. You can define it easily in LaTeX. That's how I created it. So the measure of the disjoint union is the sum of the measures. This is called countable additivity, and that's certainly a desirable property of measures. We're going to try to set up Lebesgue sums, and we'll be summing over disjoint sets, rather similar to the way you do it in the Riemann setting. You deal with those partitions and you have little rectangles over, not entirely disjoint, but over little subintervals. They only overlap at their endpoints. So we'll need this countable additivity in the development of the Riemann integration. This might look somewhat familiar. Some of these things will in a setting of probability. Probability is an example of a measure. Theoretical probability is all about measure theory. It's a branch of measure theory, in fact. So you'll see some things that remind you about dealing with events, and we might have a union of disjoint events, mutually exclusive. Isn't that the word used in the probability setting? If we have a union of mutually exclusive events, then the probability of the union is the sum of the probabilities. Same idea. Not a coincidence that the probability stuff tends to overlap with the measure stuff. And finally, we desire that M is defined, we really commented this above, defined on the power set of the reals. So we want lowercase m, a function, that for every interval, that function produces the length of that interval. It's translation invariant in this sense, it's countably additive in this sense, and it's defined on the power set of the reals. So it's defined on every subset of the set of real numbers. We'll see that we fail. We'll see in section 2.6 that there's not a function satisfying all four properties. In fact, not justifying these claims, taking Royden and Fitzpatrick at their word on these claims. There's not even a set function satisfying properties 1, 2, and 4, and replacing 3 with this condition. It's called finite additivity. If we take a finite union, k equals 1 to n, a finite union of mutually disjoint, mutually exclusives in my head, but pairwise disjoint, I should say, Finite collection of E sub k's, pairwise disjoint. If we take the measure of that finite union, we get the sum of the measures. So the claim is there's not even a set function which satisfies properties 1, 2, and 4. The measure of an interval is its length, essential for setting up something like Riemann integration. Translation invariance, defined on the power set of the reals. And instead of considering infinite countable sequences, they just consider a finite collection. If we were to replace countable additivity with finite additivity, there's not even an example of that. We'll see this later as we work our way through chapter 2, some illustrations of these claims. Definitely we'll see that what we're trying to do is not defined on the power set of the reals by demonstrating the existence of a non-measurable set. It's unknown, quote unquote, whether a measure satisfying properties 1, 3, and 4 exist. If we assume the continuum hypothesis, such a function does not exist. Continuum hypothesis related to cardinalities of subsets of the real numbers, say. We went through that earlier. Properties 1, 3, and 4. So this time they've abandoned translation invariance just to keep the measure of an interval as its length. Countable additivity, we need countable additivity. We can't get away with just finite additivity, really, and to set up integration. And defined on the power set of the reals. It's this one that's causing the trouble, and it's this one we'll eventually abandon when setting up Lebesgue measure. All right, so what we will do is we'll weaken property 4. Okay, so we'll have a measure that's measure of an interval is its length. It'll be translation invariant. It'll be countably additive. Oh, but there'll be some sets on which it's not defined. So there'll be some subsets of the real on which our measure is not defined. Okay, well, we'll just try to define the function on as large a set as possible. That is, a largest set, subset of the power set of the reals as possible. So it won't be defined on the power set of the reals, but we'll define it on a whole bunch of sets of real numbers. In fact, to find a set on which this measure is not defined, we will go to some pretty exotic set theoretic links. Exotic set theoretic arguments to establish that there's a non-measurable set. And we'll do this, it's around the end of chapter 2. There's a section titled non-measurable sets. I think it's chapter 2. But we'll go through that. It requires the axiom of choice. So that's the exotic set theoretic arguments that are needed. We're going to require property 3, the countable additivity, require that that holds. That means we're going to require that the collection of sets which are measurable, we'll denote it with a calligraphy M, that collection of sets is closed under countable unions. And we'll have closure under complements as well. In other words, we're going to define our measure, well, Lebesgue's measure, on a sigma algebra of sets. It's going to be a sigma algebra of sets that includes all intervals. In particular, it will include all open intervals. Gee, yes, we've encountered sigma algebras that contain the open intervals and the open sets before. It was the Borel sets. So this sigma algebra will include all the Borel sets as well. And in terms of describing what sets of real numbers look like, we've got open sets, closed sets, F sigma delta sets, G delta sigma sets, F sigma delta sigma, and so forth, those kinds. And the description, granted, is clunky. And that wasn't even all the Borel sets. Well, our measure will include all of the Borel sets and more. It'll include a lot of sets. The only sets it will exclude are really exotic, but there are, using the axiom of choice, non-measurable sets out there. So this is what we're up against in establishing measure theory. The book gives exercises. Some are given as homework. This first one I want to do right here, right now. We're talking about a specific measure with specific properties. Problem 2.1 says, let M prime be a set function defined on a sigma algebra A with values in 0 to infinity. Assume this measure is countably additive. So there's your hypotheses. If A and B are sets on which this measure is defined, with A a subset of B, then this measure of A is less than or equal this measure of set B. This property is called monotonicity. Monotonicity is a useful property of measure. What measure are we talking about? We're talking about, well, I guess I shouldn't even say measure. We're talking about a set function that satisfies countable additivity. Yeah, I shouldn't call it measure. Gee, it doesn't satisfy the M prime value of an interval as its length. They didn't say anything about that, so I can't assume it. But Lebesgue measure will be a measure like this, and so Lebesgue measure will satisfy this property of monotonicity. The textbook doesn't put a prime on this measure when they talk about it. I am, and I'm kind of saving the font, little italics M, to mean Lebesgue measure. This is not necessarily Lebesgue measure. Okay, so I put a little prime on it to distinguish it from that. Let's prove that. We know so little. We know M prime is defined on a sigma algebra of sets, and we know that it's countably additive over collections of sets which are in that sigma algebra. Okay, so guess what we're going to use? Let's go through a proof of it. We're going to use this very small amount of stuff that we know. And just one little proof from this section. Actually, it's a homework problem. Hypotheses. So M prime is defined on a sigma algebra, and it's countably additive. All right, so we've got two sets, A and B, which are in that sigma algebra. A is a subset of B. First, let's consider B set minus A. That is B intersect A complement. That's in this sigma algebra, right? Because the sigma algebra contains set A. A and B are sets in the sigma algebra. Okay, then A complement is also in that sigma algebra because sigma algebras are closed under complements. B is in the sigma algebra, so B intersect A complement is also in the sigma algebra because sigma algebras are closed under intersections, actually closed under countable intersections. We'll make a comment. We don't need this sigma part, it turns out, for this argument. So B set minus A is an element of that sigma algebra. I'm very conscious of which sets are in the sigma algebras and which aren't. That'll play a big role when we look at which sets are Lebesgue measurable and which might not be. Let's take set B then and write it as B set minus A union A. Remember, A is a subset of B, so all we've done here is taken the stuff in A and the stuff in B that's not in A and created two disjoint sets. We just showed both of those sets are in the sigma algebra A using the properties of a sigma algebra, actually the properties of an algebra. And we've written B as this disjoint union. B is the stuff in A, remember A is a subset of B, disjoint union with the stuff in B that's not in A. So we had hypothesized countable additivity. All right, well, where that says when you have a disjoint union, if you take the measure of that disjoint union, you get the sum of the measures. So the M prime value of B is the M prime value of B set minus A plus the M prime value of A. We've got countable additivity. We're actually just using finite additivity, ain't we? So I know the M prime value of B set minus A is greater than or equal to 0. The M prime values were non-negative. In other words, I'm using greater than or equal to in a somewhat new way, allowing that value maybe to be infinite. And of course, when I say something like this, it's understood if this is infinity, then indeed infinity is greater than or equal to 0. Notice there's no minus infinities popping up in this. There's just a single infinity symbol that has arisen. We won't do arithmetic with it because we can't. That's meaningless. But we can extend inequalities to include that infinity symbol in the obvious way. So here we've got m prime of b equals something non-negative plus m prime of a. Okay, well, then it must be that this is less than or equal to that, because to this, m prime of a, we've added something non-negative to get m prime of b. M prime of a must be less than or equal to m prime of b. And they could be equal to each other because some sets can have measure 0. But you already knew that because we went through that idea of measure 0 in the Riemann-Lebesgue theorem. So if A is a subset of B, then m prime of A is less than or equal to m prime of B. Where m prime is, I want to say it's a measure. It's countably additive and defined on a sigma algebra. Actually, we didn't use any of the countable stuff. We could have got away with saying algebra and finite additive. We didn't need the sigma stuff. The book gives you a handful of exercises in this section, and this is the setup for that collection of exercises. Let m prime be a set function defined on sigma algebra A with these output values. It's the other questions, the other exercises that need this sigma part. We only need the algebra and the finiteness part in this little argument here. So back to the notes. There's the proof of monotonicity in a very general setting. Yeah, this setting will include Lebesgue measure. So when we get around to the Lebesgue measure definition, one of its properties will be monotonicity, a useful property. Monotonicity is quite a useful property, it turns out. Another property of measure is the following. This needs some of the sigma properties. This is problem 3 from the section. It says if E sub k is a countable collection of sets in a sigma algebra A on which a countably additive measure m prime is defined, then the m prime value of the union of the E sub k's is less than or equal to the sum from 1 to infinity of the measures of the E sub k's, the m prime values of the E sub k's. This is called countable subadditivity. It means what it says. You might be fishing for the word disjoint, but it ain't there. So there's no assumption of disjointness here. If these were disjoint sets, I'd expect we would get equals the sum, not less than or equal. Yeah, well, maybe some stuff occurs in multiple sets, and when you go through over here, the weight m prime is maybe weighing some things more than once, and that's why we get the inequality. But that's the claim. You know you have countable additivity, but that's given as a hypothesis, but countable additivity only applies to disjoint collections. Here, we don't know that we've got a disjoint collection. The proof will require you to create a disjoint collection because you're going to need to use countable additivity. It's somewhat similar to the monotonicity idea we had upstairs in that we took set B and broke it into 2 disjoint parts, A and B set minus A. You have to do a similar type thing down here, but on steroids, because down here you don't have to union of 2 sets. You've got a union of a countable number of sets. So there'll be a bunch of creation of disjoint sets down there, but that's how that homework exercise will be processed. And that takes care of the introductory section. The big punchline is, I want a measure that satisfies these 4 properties. So this will be the motivation of how we define Lebesgue measure. So we'll set up a definition, we'll establish some of these properties, and this one's going to have to go. It's impossible, as we'll show, to find a measure that satisfies all 4 of these. Okay, so Lebesgue measure will satisfy the first 3. Those are necessary mechanical things, but it won't satisfy the last one. There will be sets which are not Lebesgue measurable. And they'll be very exotic sets. So we'll do a pretty thorough job of setting up the measure. And from there, we'll set up Lebesgue integration. So that will come later. But onward and upward to the definition of Lebesgue measure and some of its properties. I will see you in section 2.2. Bye-bye.